We'll use an atom optimizer as before to train our model, and since it's a classification problem, we'll use the cross-entropy loss function. I'm going to set up a little helper function to train our model. The function is called train. The model is set to the train mode, and for every batch of data in the train loader, we move the data to the CUDA device for training, and we make a forward pass through the model on line 6 by passing in the node features and the connections in the graph. We also pass in the batch vector. We compute the loss by comparing the predictions of the graph with the actual values in our dataset, data y, and we make a backward pass to compute gradients using loss, backward. We call optimizer step to update the model parameters, and we zero out the gradients in the optimizer for the next batch of training. This train function computes gradients and trains the model. Let's set up a test function that will compute the accuracy of the model in its current state on the data that we pass in, whether it's training data or validation data. So this test function takes in a loader as an input argument. We switch the model to the evil mode so no gradients are computed, and we initialize correct to 0. We run a for loop for every batch of graphs in the loader. We move the graphs to the CUDA device for training, and we make a forward pass through the model using its current weights. The out variable gives us the model's predictions, and we get the actual predictions by using the Rmax function, that is the index of the class or category, which has the highest probability score. On line 11, we compute the number of predictions from the model that match the ground truth labels in our graph, dataset, and increment correct by that amount. And on line 13, we compute and return the accuracy of this current model on the dataset that we've passed in. Let's go ahead and train this model. Now on lines 3 through 5, I once again initialize the GCM model, the optimizer, and the criterion. This is not really needed because we've previously initialized all 3 of these earlier. However, I've included it in the same code cell as the training code so that you can retrain a new model if you just want to see what's going on. So each time you execute this code cell, you'll create a new model for graph classification and set up the optimizer and loss function for that model. I initialize best val accuracy to 0 and best model state to none. We'll use this to track the model weights of the best model based on its accuracy on the validation data. Next, the model training code will train for 200 epochs. That's a for loop on line 10. Just invoke the train method to train the model for all of the batches in the training data. Once we have train model for the current epoch, I've invoked the test function and passed in the train loader and the validation loader respectively to compute the accuracy of the current model on the training data and the validation data. On lines 15 through 17, if you find that the validation accuracy is better than the best validation accuracy we've seen so far, we make a copy of the model parameters. And on lines 19 and 20, for every 10 epochs, we print out the epoch number, the training accuracy, and the validation accuracy. Let's go ahead and start the training process, and you can see that at the very end, we get a validation accuracy of about 74%, but let's see what the best validation accuracy was. I think it's about 75. And let's update the model parameters with the best model. So the model with the best validation accuracy of 75.5, that's the model that we are going to use on our test data. Let's now compute the accuracy of the model's predictions on the test data. Make sure the model is in evil mode. The code on lines 2 through 11 is code that you've seen before in the test function. This is where we iterate over the test data. We get the predictions from the model from the test data. We see what predictions are correct that is or equal to the ground truth values and compute the accuracy. Let's print out the best test accuracy here, and you can see it's 70.9. Not bad for our graph classification model. Keep this accuracy number in mind. We'll see if we can improve the performance of this model by using a different layer in our neural network architecture.